Hi everyone, let's start section 2 of chapters 7 and 8. So at first we'll have the section 2 of chapter 7 and at the end we'll have chapter 8. And this is the first part of the videos. In section 2 of chapter 7, we'll have the test methods to test if the random numbers generated are based on uniform distribution and also they are independent of each other. As you remember, we had these two main properties, uniformity and independence for any random number generator method. So here we're going to learn the test methods to test these two properties. And so the first one is for the frequency test, the uniformity test actually. So here we have a hypothesis test here. The H0 is this hypothesis that the random numbers are based on uniform distribution between 0 to 1, and H1 is against this hypothesis. So here we have two test methods, the Kolmogorov-Smirnov test, or in short KS test, and also chi-square test. Okay, and for the independency, we have an autocorrelation test here. So again, we have this hypothesis. H0 is that the random numbers are independent of each other, and H1 is against this hypothesis. So yeah, here we have a method to calculate a criteria and then test it against 0 to see if there is any correlation between the random numbers. The first method is a Kolmogorov test, or KS test, for uniformity. So in this test, actually at first we sort the random numbers in ascending order. So R1, R2 to Rn, they are in ascending order. And then each of the assorted random number will be checked for deviation from the uniform distribution, and then we'll calculate an absolute deviation as an statistics, and then it will be compared with a critical value to see if we can accept the H0, the hypothesis that the random numbers are uniform or not. In KS method, we are going to compare the CDF of the uniform distribution with the empirical CDF of the sample of random numbers, which we call it SNX. So the SNX will be calculated by this equation here. So we actually consider an X, and then we count the number of random numbers which are less than or equal to that X, and then we divide this number by the total size of the sample of the random numbers, which is capital N here. So here we calculate the SNX for each X, and then we do have the FX, the CDF of the uniform distribution for those X's as well. Then we can actually calculate the deviation between the actual CDF, FX, and the empirical CDF, which is SNX, right? And then we consider the largest absolute deviation between fx and snx, and then we will have this actually. Okay, so as you see here, we consider the maximum absolute deviation between fx and snx. If we assume d here as a random variable, so the sampling distribution of d is known, and it's tabulated as a function of n in table A8. So we'll use that table AN as a reference, and then we can obtain the critical values for any confidence level. And then by having those critical values from that table, we can actually analyze our hypothesis test here. Okay, so yeah, this is the main idea of the KS test. So here we have the steps of the KS method. At first, we need to rank the data from smallest to largest. So as we sort them in ascending order, okay? And then we compute the deviations. So here we calculate two let's say maximum deviations, D plus and D minus. So D plus is the maximum deviation if we subtract the true value, I mean the actual CDF or I from the I over N, which is SNX, okay? And D minus is the maximum quantity if we subtract I minus 1 divided by N from RI, okay? So, and then the D will be considered as the maximum between D plus and D minus. And now, so we have our statistic here. So we need a critical value, which is D alpha. So by having an alpha, a significance level alpha, we go to table A8, and then by having that alpha and also the sample size N, we can obtain the critical value of D alpha. And then we compare the D with the critical value of D alpha, and if D is greater than D alpha, we should reject the null hypothesis. Other than that, if D is less than or equal D alpha, we'll conclude that there is no difference between the true distribution of the random numbers and the uniform distribution. Okay. This is the table A8. So as here we have the values for alpha of 0.01, 0.05, and 0.10. So the most common one is 0.05. I mean 95% of confidence level. So yeah, as you see here, we do have the values for n going from 1 to 35, and over 35 we have these formulas, you know, in order to obtain the critical values. Okay. Let's have an example here. Here we have these numbers, 5 random numbers. So if we sort them in ascending order, we will have this sequence: 0.05, 0.14, 0.44, 0.81, and 0.93. Right? So by having this these random numbers, we can calculate the values in order to obtain D plus and D minus. So for R3, for example, we have I over N minus I3, right? And also we have R3 minus I minus 1 divided by N, right? For R3, for example. So here we have this calculation. As you see here, I divided by N becomes 3 divided by 5, 0.6 minus 0.44, it becomes 0.16. So we need to calculate the same, quantity for all 5 numbers. That's for just for the third number, for the all 5 numbers, and then take the maximum between those ones, which becomes D plus. As you see here, the D plus is this number, 0.26. Okay, so yeah, the D plus here becomes 0.26. And the D minus, oh, one thing here, as you see here, we for calculating the D minus, we consider I minus 1 divided by N instead of I over N. The reason is here, if we consider I, then the last number always will be 1, right? But as you know, for continuous distribution, the probability of having an exact number in a continuous range is 0, right? So the probability of generating the value of 1 in a sample of random numbers it's zero. Actually, it's almost zero. So because of that, we need to consider I minus 1 over n in order to skip that situation that we never generate the value of 1 in any size of sample random numbers. Okay, and the d minus is 0.21 here. So yeah, d minus 0.21. So the d, which will be the maximum between d plus and d minus, will be 0.26, right? So we have the statistic here and we need a critical value. Let's say we are assuming alpha as 0.05. This means that 95% confidence level. So if we go to table A8, the D 0.05 and 5, I mean n as 5, will be this number 0.565. And as you see here, the D is less than or equal to D alpha, right? D alpha. Therefore, our conclusions do not reject H0. This means that we can't actually reject H0, so we can say there is somehow uniformity between the generated random numbers. So we can say they are somehow from a uniform distribution between 0 to 1. Okay. So yeah, that's it. And in the next part, we will have the chi-square method for testing the uniformity. Okay, thank you.